Hello and welcome to this new video where we discuss things physics and mathematics on the board. In this video, what we are going to look at is basically the potential one form, so that's in exterior calculus, and this is part of a series of videos where we actually look at characterizing and framing electromagnetism or electrodynamics even in the context of exterior calculus and show what are the advantages and benefits if we basically do that. Here, in that case, the electromagnetic potential is described as a one form. So you can basically see the corresponding video. This is something you haven't seen before. Perhaps this is going to be to give more context to it. Notwithstanding this kind of remark, what we are going to do in this video is basically check that this particular quantity is actually invariant under Lorentz transformation. What that means is that it's invariant under a change of inertial frame of reference upon basically or in special relativity. Right, okay, so just to put a little bit of context here, this is the one form we are looking at. And in principle, we are relatively agnostic as to how this form is going to look like and behave. However, if the frame of observation R, for example, or F, whatever you want to call that, is fixed, let's say, and there is another frame moving with respect to it at some velocity u in the x direction, then you're going to have the following Lorentz transformations for the x and t components of dx and cdt here. So you're going to have gamma and then factorize dx prime plus beta cdt, actually cdt prime. And then here cdt is equal to gamma and then cdt prime plus beta dx prime. Now, in case you're a bit confused about where to put the c's, you just need to have the dimensions to be okay, throughout the equation. Okay, so that's a good way to know where to put the c in case you forgot. And the y and z coordinates are actually unaffected by this particular change of frame of reference, and therefore we shall not kind of consider them. I mean, they are here, but in the calculation we are going to look at, we are going to focus on the two other components here. Now, gamma is this Lorentz factor, so that 1 divided by the square root of 1 minus u squared over c squared, and then beta is equal to the ratio u over c. Okay? Now, what I'm going to suggest here is that the field transformation for the potential is like this. And what I would like to illustrate is that if it follows that particular transformation rule, then this is going to be Lorentz invariant. Okay, so let's try to have a go at it. As I said, just because of space, I'm going to kind of ignore for most of the derivation these terms because they actually don't change. So I'm not going to essentially look too much at them. So let's look at the first two aspects of it. So A is equal to minus V dt and then plus AX dx. Now, what you could imagine, I'm just going to focus on these ones. You can simply imagine that, let's say, AY and AZ are 0, for example, just so that I can kind of move on with the calculation. So now what we do is simply, I'm going to put a 1 over c here and a c there for c dt, so that I'm in line with the kind of expressions I'm going to find here. And then basically we can move on with applying the transformation rules. So here we've got gamma. So V over C is equal to gamma. And then we've got V prime over C. And then plus beta A prime X. Okay. And that's time C dt. Okay. And C dt is here. So that's times gamma, so that's going to be a gamma squared. And then I've got c dt prime, and then plus beta dx prime. Okay? Then I've got this ax prime here. So then we've got plus, so ax is gamma, and then ax prime plus beta v prime over c, and that's time dx, and dx is equal to gamma. So again, I've got gamma squared here, and then we've got dx prime, and then plus beta and c dt prime. Okay, so the goal now is simply to expand all that and try to see where we land with this. So where we land with this. So first of all, we are going to get minus gamma squared. So we still are with gamma squared here. And then we are going to get this expression. So here we're going to get v prime dt prime. Okay. Then we are going to get v prime over c. So plus v prime over c beta beta dx prime, then plus beta a prime x c dt prime. Okay, and then plus beta squared, and then a prime x, and then dx prime. Okay, so that's the first series, so that's the first terms here. Then let's look at the other ones. Gamma squared, and then we are going to have a prime x dx prime. Okay, then we are going to have plus a prime x beta c dt prime, and then plus beta beta v prime of c dx prime, and finally plus beta squared and beta squared v prime dt prime. Okay, so what we can see here is basically what are the terms that are going to be identical. And I've got these product terms, right? So a prime x beta c dt prime with a plus and a gamma squared here. And here I've got the same, but with a minus there. So actually this guy is going to cancel out with this one, okay? Then I've got another mixed term, which is this one, v prime over c beta dx prime minus gamma squared, and that's going to be compensated by this one, beta v prime over c dx prime plus gamma squared, okay? And basically that's it. So what I have got left is the following. I'm going to get that I've got gamma squared, and then let's factorize, so let's say v prime dt, and then that's factorized by 1, in fact that's not 1, that's beta squared minus 1, okay? And then I've got plus gamma squared, and then a prime x dx prime, and then 1. So you see, I've got here, where am I? I've got, yes, I've got a plus here, so I've got a 1 minus and beta squared here. Okay? Now, as it turns out, beta is u over c. So 1 minus beta squared is 1 minus u squared over c squared. But this is actually 1 divided by 1 minus beta squared. Okay? So the bottom line is that, as you can see here, you've got that gamma squared and then is equal to 1 divided by 1 minus beta squared. And basically that's what we've got here, gamma squared times this. So at the end of the day, we get that this is v prime dt prime and then plus a prime x dx prime. Okay, as required. If you were to put then back, if you want, the unchanged part, you could. That was just to show that this part is actually invariant indeed. What that means is that if you know the components of the field, sorry, that's a minus here. If you know the components of the field, so in particular inertial frame, then basically you're going to get a specific value at some specific location and so on for that particular one form. And the bottom line is that if you change the frame of reference, you're going to get the same value, okay? Because that's still the same A you're going to see, okay? So that's really the crucial aspect that we want to care about here. That's what invariant means in that context. It is covariant in the sense that it reads the same way, but the actual value you would find would be the same as well, okay? Because these things essentially kind of are written in numbers in a sense. Okay, so basically that's the only thing that I wanted to discuss, that essentially this is the same as the original A we started from, which was simply in a different frame. So the values would be, again, the same. All right, so I hope this was kind of easy enough to follow. And then if not, please do let kind of put some comments, and then I will be happy to answer the questions. And otherwise, see you in the next video.